So we were talking about, you know, trying to, we have the acid chart. One thing you want to do when you look at the acid chart is look for patterns. Are there any patterns in there? And the only time you would be able to see the patterns is if they're very simple patterns. But normally to recognize patterns, you look at the material over and over again. You know, you almost kind of memorize it. You don't really memorize. You don't have to memorize that acid chart. But you've looked at it so many times that, you know, you can kind of get a hunch that, okay, you see this acid or you see this base, you can kind of get a hunch, you know, that could be a strong base. You know, like sulfide, I don't know. When I wrote sulfide on the board, did anybody pop in their mind that, oh, yeah, strong base? Did anybody? You know, and if not, you know, you just look at that chart more and more, you know, like amide. You know, those types of things. So you want that to register, and then, you know, getting that to register is a major step up, because then you see things that might be similar looking, you know, and then you can kind of place them based on a pattern. Well, that kind of looks like amide, you know, just a little bit different. Maybe it's going to have similar properties. Or it kind of looks like ammonia. Maybe it has similar properties. And so this is pattern, but extending the pattern out to things you haven't seen before. Right, and so a lot of people say, "Oh, that, you know, I never saw that. You know, I never saw that base. I never saw that acid." Well, then I know you're still at this level. You haven't gotten to this level, right? When you get to this level, then you say, "Oh, that's very similar to this, which I saw here," right? And so you're looking for those types. You're looking for those types of things. But, you know, a lot of people say, yeah, I don't want to memorize anything. Memorizing is just not for me. You know, I'd rather just look it up, you know, Google it or something, or just have a thorough theoretical understanding of it. But, you know, I asked you the theory of chemistry. You know, how many of you have a thorough theoretical understanding of chemistry? Probably not much, right? Not much. And so what we want to do is we want to develop a better theoretical understanding, but theory is not easy. You know, it's very difficult. It can be very challenging. But we'll insert some theory here and there, and that will help ease the burden of memorization, but there are limitations to theory. Do you guys know what equation chemistry is based on, pretty much? Schrodinger equation. Good. Are you guys very familiar with Schrodinger, or you just heard the name, you know? Or maybe not familiar at all, you know? And so we're at the memorization stage, right? We don't have the tools to use theory yet. But actually we do. We have a lot of tools that we can use theory, because this Lewis symbols, where did that come from? Quantum, right? You know, valence electrons, core electrons, that type of stuff. Lewis structures, same thing. And so we actually have a lot of what I call theoretical tools. We just draw out the structures and then just analyze it like this. And so here's some analysis of identifying, actually this is the wrong one. All right, this one. Identifying Bronsted acids. We talked about inductive effect. We talked about, you know, things that could help us quantitate the inductive effect, things like oxidation state, right? That type of stuff. And so this is, you know, what we can do using theory to approach it. Lewis structures, bonding, all that stuff. And this is why I want you to review that stuff. And yeah, a question often comes up: what do I need to review from Chem 1A? Well, if this stuff seems okay, you know, you're good with it, then that's you're good so far, you know. But if this stuff seems a little fuzzy, then you need to review it. You need to review it so that you understand it. And so, if I asked you what the definition of oxidation state is, you'd tell me. If I ask you compare and contrast oxidation state with formal charge, you could do that. Somebody said, what is the definition of oxidation state? Oh, it's this mathematical equation. I don't want a mathematical equation. I want, you know, a description of it. Because let me tell you, do you have to be a PhD to solve the ideal gas law? No. Do you think an elementary school kid who's doing algebra could solve the ideal gas law? Sure. With zero chemistry background. Zero. Right? But will an elementary school kid tell you, what the assumptions are in the ideal gas law? What are the assumptions in the ideal gas law? What are the limitations in the ideal gas law? If you calculate the pressure of hydrogen gas and compare it to the pressure of CO2 gas, are both calculations equally as accurate? No, you know that, right? Because hydrogen's more ideal, CO2 is less ideal. You know that type of stuff, and therefore, that's the type of stuff that we want. We don't want, I can punch in the numbers, because anybody can do that. And so anybody could calculate an oxidation state, but not anybody can tell you what it means. Right? And so that's what we need. And so we're going to be using that type of stuff for this, because oxidation state tells us electron distribution, and acid-base properties depend on the electron charge distribution. We can see that here in the electrostatic potential maps here. And so these are from quantum mechanical calculations using computers. And we could do that, but quantum mechanical software is expensive. So somebody says, I don't want to memorize this stuff. I don't want to have to figure it out using Lewis structures. I just want to do it on my computer, do a calculation. Well, it's going to cost you, right? This software is like, I forgot, $5,000. All right, so what we want to do is we want to determine electron density distributions. This is why we need to know how to distribute the electrons in a structure. And since we can do this on pencil and paper without buying expensive software using the 3 ways of counting electrons. Do you know what the 3 ways of counting electrons in a molecule are? Tell me the 3 ways you can count electrons or distribute electrons in a molecule. The 3 ways that we use. Octet, formal charge, and oxidation state. And so what you need to do is you need to go back and look, what is the difference between octet, formal charge, and oxidation state? And then when we analyze these structures, we use all of those, to kind of come up with a visual picture of what or how the electron density is distributed. And so here, determining electron density distributions, quantitative, we just use quantum mechanics and software and computer calculations. But qualitative, semi-quantitative, we use counting electrons. We could do this with pencil and paper and our understanding of theory. Okay, the 3 ways are this, octet, formal charge, and oxidation state. Now, the reality is octet is not. Octet is something separate, but 2 and 3 tell us how the electrons are distributed in there. Are the electrons distributed evenly, unevenly, right? How are the electrons distributed amongst the bonding atoms? And so here, it turns out that the reality is not really formal charge or oxidation state. The reality is more like bond polarity. And so this would be the 4th, the composite formal charge and oxidation state. Somebody tell me, formal charge assumes what?
100% covalent.
100% covalent. Oxidation state assumes 100% ionic. And as you remember from bonding, there's a percent ionic character, percent covalent character. It's not necessarily 100% covalent. It's not necessarily 100% ionic. It's somewhere in between, right? And so the actual charge distribution is going to be somewhere in between, and we call that bond polarity, but we just want a more, how do you compare, delta plus and delta minus? Sometimes they're easy to compare, delta plus here versus delta plus there, right? But, comparing these delta pluses, which are judgment calls, we can do the calculations using quantum mechanics, but comparing the delta pluses isn't easy. And so what we do is we compare formal charges with formal charges, or we compare oxidation states with oxidation states. And then it makes it useful. Even though these aren't accurate, they're still incredibly useful in describing the properties. All right. The next category, we're going to be talking about this as we go along, how to analyze structures and this type of stuff. But you should review, did you cover the last part of chapter 16? 16.7 and 16.8 in Chem 1A? Did everybody do that, or who didn't? Okay, yeah, I guess everybody did that. So you would review that, because that would talk about a lot of this stuff as well. All right, when we do Lewis acid-base reactions, Lewis acid-base is the most general. And we don't need Bronsted, because all Bronsted reactions are also Lewis reactions. So we could skip Bronsted entirely, but Bronsted are a heck of a lot easier, because Lewis, you have to really analyze the Lewis structure to see. Now, an acid is defined as an electron pair acceptor. A base is defined as an electron pair donor. And so take a look at this reaction here. We have ammonia. Ammonia is a Bronsted base, but it's also a good Lewis base. In fact, ammonia turns out to be a very powerful Lewis base. As far as a Bronsted base goes, is it very powerful? No, it's a moderate base, right? It's not exceptionally powerful. But it turns out to be a pretty powerful. Now, Lewis bases, this is what happens in the Lewis acid-base reaction. Here's our base. Our base attacks our acid. What's special about BF3? Organic chemists, I got this from organic. Organic chemists fail to write lone pairs unless they really need to, because they figure by the time you hit organic chemistry, you'd know how many lone pairs on fluorine. How many? 3 lone pairs, right? And so this is why the lone pairs are missing. But for general chem, I want you to write the lone pairs here. This. All right, so BF3, what's unusual about BF3? You guys learned this in Chem 1A.
It's not an octet.
It's not an octet. Why don't I just form a double bond?
Fluorine can't.
Yeah, fluorine can't double bond. That's a rule. Why can't fluorine double bond? It's too electronegative, because if fluorine forms a double bond here, then boron would get what formal charge? Right now, all the formal charges are 0. But if fluorine formed a double bond, then boron would get a negative formal charge, and fluorine would get a positive formal charge, which tells you that fluorine just lost an electron to boron. Does that make sense? No. But there was one that didn't make sense, but it happened. And that was with carbon monoxide. You guys remember what happened in carbon monoxide? Carbon monoxide has a carbon-oxygen triple bond. And the formal charges are very weird on carbon monoxide. Right? Carbon monoxide has weird formal charges. Why? Oxygen lost an electron to carbon. This happens. This happens to get the octet. Otherwise, you can't get the octet. But in BF3, does it happen? No, fluorine is just too strong, too electronegative for this to happen. And so this is an unusual one. Now, if you think about electrical interactions, bases are, negative or positive, you think, in terms of charge density. Negative, and acids are positive. In fact, this is what we'd call kind of electron poor, because it doesn't have an octet. Even though boron tries to pull an electron from fluorine, it's not going to be successful. But in this particular reaction, look at nitrogen comes in, there's a lone pair, and it can bond here. Now the formal charges are kind of weird here, but it's okay because now we got the octet. Only fluorine's the one that can't have these weird ones. But here nitrogen is positive, now boron has a negative, but everything has a octet. Okay, the bond that forms is this. This is kind of a combination reaction. Do you see A plus B yields C? But it's a Lewis acid-base combination reaction. We have redox combination, acid-base combination. A metathesis could be thought of as combination if you got like a magnesium ion coming with a carbonate ion. As a combination, the best one to know is the element plus element combination. But anyway, going from here to here, it's kind of a different type of covalent bond. The type of covalent bond, a normal covalent bond is you have an electron from hydrogen, they come together and share, right? This is a normal covalent bond. But in this case, in this covalent bond, both bonding electrons came from nitrogen. And we call it a different name. We call it a coordinate covalent bond or dative bond. A coordinate covalent bond or dative bond, just to indicate that both electrons came from nitrogen. Now, you can't always tell, you know. It just looks like any other covalent bond. This would be a polar covalent bond, right? That's it. Polar covalent bond. And so once the dative bond forms, dative, D-A-T-I-V, or coordinate covalent bond forms, you can't tell the difference between a normal covalent bond and one of these. So what we do is we analyze, you know, this would be called the acid site here. This is the base site. We just analyze it. So let's analyze Lewis acids and bases. Looking at the structure. You look for electron-rich regions. Electron-rich regions that have a lone pair. Electron-rich regions that have a lone pair should be your base sites. And then you look for electron-poor areas that can accept a lone pair. Now, electron-poor areas that can accept a lone pair would be called your acid site. Now, how can they accept a lone pair? Does everything have to have less than an octet? No. What can happen is this. If the base is strongly attracted to the acid, the base will come in and attack the acid and push out electrons. If electrons can get pushed out, because sometimes we cannot exceed an octet, right? In fact, most of the times, you've seen, we don't exceed an octet when we're dealing with second period. We'll never exceed an octet. And so capable of accepting electron pair, we'd look for that. Now what we're forming is a coordinate covalent bond. Now how would you describe a coordinate covalent bond? Well, there are different ways of describing coordinate covalent bonds. There are two ways. What are the two ways of describing a coordinate covalent bond? This bond can be described as
Both electrons coming from.
well, yeah. Well, both electrons are going to be coming from there. But how do you describe a bond? We have two theories to describe a bond, right? You can describe it as. Just tell me what this bond is. Describe this bond to me. Even though both electrons came from nitrogen, we'll ignore that and just call this a. What kind? sp3 sigma bond, right? sp3 sigma bond. One of the things we look for, actually, in addition to reactivity of the reactants, like is it a strong acid or weak acid? We also look at, in reactions, we look at the stability of the products. And so when we do this, we need to know, how good of a bond is formed here, right? What kind of bond. And so we could describe it in terms of valence bond theory. It's a simple sp3 sigma. Or we could describe it in terms of MO theory. How would you describe a bond in MO theory? Just give me a quick review because, let me tell you why I like to review stuff. One, because we need to use it. And two, because I know I told some of the Chem 1A people this, but you know, my friend, his biology major, asked me for help to reviewing chemistry. Do you guys remember this? He asked me for help reviewing chemistry. So I said, sure, no problem. I'll help you. And then when I sat down with him, he was like a blank slate. I mean, just like empty pages. Nothing. He remembered absolutely nothing from chemistry, almost. And then I thought, no, there's no way, because there's not enough time to review that much stuff in time for this year's MCAT. And so he ended up taking a year off to review. A year off because he forgot everything, basically. Well, it's easy to forget if you never use it, right? And so let's try to use some of the stuff you learned in Chem 1A. Well, therefore, how do you rate the strength of Lewis? Rating the strength of Lewis acids is a heck of a lot more difficult. The reason it's a lot more difficult is you got to look at the molecular orbitals that are formed, or the orbital overlaps that are formed. And that depends on the orbitals. You know, for example, what forms good strong bonds? And what forms good strong bonds is if you let's take a tiny sp3 and overlap it with a gigantic sp3. Is that going to form good orbital overlap there? No. You want a tiny sp3 and a tiny sp3. That's good orbital overlap. It's going to concentrate the electron density there. And not only that, if you take an sp3 and an sp3 and you do a, what do they do in MO theory? What's that thing called that starts with an L? What's that thing called that starts with an L? Acronym is LCAO. Somebody tell me what the acronym stands for. Linear combination of atomic orbitals. If you do a linear combination of atomic orbitals with small sp3, you can do linear combinations of atomic orbitals with hybridized orbitals too. Hybridized atomic orbitals to get like the sigma sp3. Rather than the sigma s, like the sigma 2s, you get the sigma sp3. MO. And so it turns out that looking at the MO theory, and this is, you need MO theory to rank these. Right? And so looking at the MO theory, one guy came up with a pattern, very famous chemist. And the pattern that he came up with, he called HSAB, hard, soft, acid bases, depending on, you know, their orbitals. And so like small sp3, those are two hard species coming together. Hard acid, hard base. Right? So hard is good. Hard, soft, not so good. But soft is good actually. Soft is good. Reactive. And so it depends on what you're reacting that. If you take a hard base, it depends on what acid you're attacking. Are you attacking a soft acid or a hard acid? That's going to change its reactivity. This is why I skip Lewis acid bases in Chem 1A. You know, I thought I'll just wait. But sometimes I cover it in Chem 1A, so I've used these PowerPoints in Chem 1A, but sometimes I don't. Oh, I didn't. Did anybody cover this kind of stuff? Lewis acid bases? So the problem is you know that acid chart I gave you? The acid chart I gave you is only for Bronsted. The acid chart I gave you is just for, okay, the acid's always the same. It's H plus, right? But in Lewis, the acids can be very different, like BF3. BF3 is what we call a powerful Lewis acid. That stuff is very reactive. It wants to get an octet. And any Lewis bases around, it'll get attacked easily, including water. And so we don't have simple things to tell us, and so we just analyze these on a structure-to-structure thing. Now, there are certain types of Lewis acid-base reactions where we can kind of come up with a scheme. You know, I told you ammonia is a kind of a weak base, a weak to moderate base in Bronsted, but in Lewis it's often thought of as a strong base. And the reason it's thought of as strong base is because if you react it with metal cations, it's very reactive. You know, and we'll talk about that soon. And so there is a ranking, but only for a specific type of Lewis acid-base reaction. The specific type of Lewis acid-base reaction is called a coordination complex reaction. Complex reaction. And so let's do this. Carbon dioxide is bubbled in water. And so first let's analyze carbon dioxide. Okay, what do we want to see? There are different ways we can analyze carbon dioxide. Let's go ahead and look at the formal charges. Do the formal charges tell us anything? No, because all the formal charges are 0. So it just has everything evenly distributed. But that's not really the case because formal charges assume the bonding is 100% covalent. Would you expect it to be 100% covalent here? No, because carbon and oxygen have different electronegativities. Good. Now, what about the oxidation state?
-2 for both oxygens.
-2 for both oxygens and +4 for carbon. And so oxidation state assumes what? 100% ionic. Is it 100% ionic? Is this ionic? No. And so the reality is somewhere in between. We call it delta plus and delta minus, right? Polar. But, you know, having these numbers here gives us a better way to compare things. And so even though this is not 100% accurate, we're still going to use these numbers to compare because we're leveling, you know, we're normalizing it. We're normalizing everything to 100% ionic unless they're homonuclear atoms in the bond, the same atoms in the bond. And then compare. And then it works. It works to tell us a lot about the chemical reactivity. Now, we use this in redox. In Chem 1A, we would say that is carbon dioxide an oxidizer or reducer?
Oxidizer.
You would consider an oxidizer. Could it be a reducer?
No.
Not really, because carbon is what we call the max. You know, it's lost all its
Electrons.
valence electrons, right? And oxygen, does it really want to lose? No, oxygen's happy as is at -2. You can compare water. Water, is it a good reducer? No, water is very stable, fairly stable. I mean, it could react with sodium, right? But it's acting as an oxidizer in that case, not a reducer. And so oxygen is pretty good as is. So this could be an oxidizer. Does everybody see that? No? For example, if carbon were to lose another electron, it would go to carbon +5, which would mean we'd have to rip a core electron out, and that would be about 10 times more energy. It's not that it can't be done, right? I mean, if you work with exotic species, you know, very reactive species, then you might try to do that. Obviously, it can be done because how do they measure it anyway? They knocked it off. People knock off core electrons all the time. There's something called, in analytical chemistry, you know, X-ray fluorescence spectroscopy, where they try to get the elemental composition, like on the lunar lander. They want to see, you know, what elements are found in this rock. And they'll blast it with X-rays to knock core electrons off. And then the valence electrons or higher energy core electrons drop back down and emit X-rays. And they give a characteristic X-ray emission spectrum. All right, so we use these in redox chemistry, but we can also use these in acid-base chemistry. Just like formal charge, we could use when there is a formal charge, we can use that to determine acid-base properties. First, we look for a formal charge, like a negative formal charge. If I see a negative formal charge, I'd be thinking maybe it's basic right there. Well, going here, I would say that what would be the base site? What would be the acid site? Carbon should be the Acid site, oxygen should be the problem with carbon is it's got an octet, right? It's got an octet, so how could it accept another electron?
The pair will be nothing.
Right. If a pair of electrons comes in here, the double bonding electrons will be knocked out into a lone pair. You see that? Let's go to water. You can do the same thing for water. All the formal charges are 0. But the oxidation states? Okay, now the same thing. We could look at these numbers for redox, or we could look at them for acid base. If we look at them for acid base, what are we looking at here? We're looking at oxidation. Now we don't always have to do this. You know, we could also just use bond polarity, for example, like this. And so, you know, the other alternative is just look, delta minus, delta plus. Now this should be the more acidic, this should be the basic, right? Lone pair. The same thing with water. We could just do delta minus, delta plus, delta plus. And so this should be the base, this should be the acid. Now how could that hydrogen accept the lone pair? The only way that hydrogen can accept the lone pair is this. This is what kind of bond is this? Yeah, it's a sigma, but just use valence bond. It's an sp3 s sigma bond. And so if a lone pair of electrons goes into this s orbital, it kicks these electrons out into the sp3 orbital. Does that make sense? And so we'll look at that right now to see what we're going to do for this. And so we have two options here, and we consider them both. Which one do you think is more likely? Option 1. This, and we do it this way. We always have the base attack the acid. And so what lone pair is that? Is that a sp3 lone pair or sp2 lone pair? This sp2 lone pair, it's sitting in an sp2 orbital. So this sp2 orbital gets pushed into this s orbital and kicks these electrons out into the sp3 orbital. And so it forms a bond here, sp2s, and breaks a bond here. Does that make sense? And so this is 1. And so we need a collision, right? There's got to be a collision. This oxygen collides with the hydrogen, forces the other electrons out. Okay, option 2 is this. Option 2 is these electrons here get pushed into carbon. And so these are what? sp3 electrons get pushed here. Now we have sp and we have pp, right? We have sp, sp2, sigma, and a pp pi. So we're going to break the pp pi and then rehybridize this oxygen to sp3 and rehybridize the carbon to sp2. Okay. And so this would be option 2. And so what you do is you just try both and see which one leads to a reasonable product. And so it turns out that option 1 dead ends. Dead ends because we don't end up with anything reasonably stable, right? And I don't want to spend too much time because I need to move on with this. And so then we try option 2, and option 2 can potentially yield something that's reasonable. What's reasonable? Something that has a Lewis structure that looks okay. And so if we do option 2 here, this is what's going to happen. Yeah, actually I did this already in 1A. You guys remember this? Yeah, you're right.
Is something else to consider how big the delta plus is on carbon as compared to hydrogen on water?
We don't. You don't actually think about what is the magnitude of the delta plus. You think it's like 0.8, 0.6, 0.5. No, don't really. Certain things can factor in. I mean, you know, a +4 here versus a +1, we can't compare those directly. When we have oxidation states, we can only compare +4 on carbon versus a +2 on carbon versus a 0 on carbon, that type of stuff. But we don't cross compare because it makes not unless you have a lot of experience with it and seen a lot of these. All right, hey, does this look like a good Lewis structure to you? No. It looks pretty bad because of the octet rule? Octet rule's been violated? No. Octet's good. So if the octet's good, then it's good, right? No, the formal charge is all screwed up. Tell me the formal charge on this oxygen. +1. Or just plus, and the formal charge on this oxygen? Minus. And so basically one oxygen lost an electron to the other oxygen. Does that make sense? Now, if there's a tug of war between two oxygens, which one wins? It should be a tie, shouldn't it? And so this is unstable. This kind of separation of charge would be unstable. And so what it could happen is it could just revert. This lone pair drops back in here, this bond breaks, and we're back to CO2 and water. And so this is a reversible reaction here. Or something else could happen. You know, temperature is a measure of what?
Energy.
Yeah. What kind of energy? Thermal or? And what is kinetic energy? Energy motion. And what types of motion do you find in chemistry?
Vibration.
Vibrations, rotations, and translations, right? And so let's think about the vibrations here for a minute. Are all the vibrations, let's say this is at 25 degrees C. Are all the molecules at 25 degrees C vibrating with the same vibrational energy? No. What do you expect to see? You expect to see what do we call it? You expect that not everything has the same energy. It's like a glass of water at 25 degrees C. Does a glass of water at 25 degrees C, every single molecule of water has the exact same energy as every other molecule? No. You expect to see a range or a Min? A normal distribution? No, it's not a normal distribution. A normal distribution is a bell-shaped curve or Gaussian. We call it a different kind of distribution. What did we call it? It's not a normal distribution. Somebody tell me what kind of distribution it is. You could call it a thermal distribution. That's fine. Thermal distributions is the common name for it. But we called it started with an M.
Maxwell-Boltzmann.
Maxwell-Boltzmann distribution. Do you guys remember the Maxwell-Boltzmann distribution? Looks like this. It's kind of like a normal, except it has a higher energy tail on it. Maxwell-Boltzmann's the fancy name for the speed distribution of gas molecules in chapter 6. Do you guys remember that? The speed distribution? Not every molecule is moving at the same speed. Well, speed is translational kinetic energy. Ideal gases have no vibrational, they have no rotational. When we're dealing with real substances, there's going to be vibrational and rotational, and we're going to see the distribution like this kind of thing. And it's going to be chopped up because it's quantized as well. Vibrations are quantized. Translations, are translations quantized?
No.
Translations are continuous. You know, it can move at any speed. But vibrations and rotations are quantized. There's jumps. But anyway, going back to this, here. let's say we just have a very strong vibration, and this oxygen collides with this hydrogen. Big vibration. And so this lone pair, which is this sp3 lone pair, gets pushed into this s orbital, kicking out these electrons into oxygen's sp3. And so this is called a intramolecular reaction. Intra means within the same molecule versus inter. This would be intermolecular reaction. This is an intramolecular reaction. This type of intramolecular reaction actually happens quite a bit, and so they give it a name. They call it a proton transfer, intramolecular proton transfer. And so here, this gets pushed into here. This gets pushed out to here. And so what forms? This is reversible as well. What is this? H2CO3. What's H2CO3 called? Carbonic acid. Now, carbonic acid, is it very stable? No, we know it decomposes. But this is why, you know what the pH of our water is? Our DI water? What is, somebody tell me the pH of our DI water. Our DI water is lower than 7. And does anybody remember that number? Chem 1A? What did you guys get for the pH of the DI water? It came out to like pH 4.5, pH 5. I wrote the numbers on the board. There was a range of values that people got. If you guys did this, did you guys do the pH? Anybody not do that? You didn't? Do you guys know what pH is? Okay. A pH of 7 is neutral. Any pH lower than 7 is acidic. And so our DI water is acidic. Do you know why it's acidic? Because carbon dioxide and air it saturates our water. Our water storage tank's up there, and we don't have it isolated from the CO2. So the CO2 gets in there, and it just creates a little bit of carbonic acid, which makes our water acidic. But carbonic acid in 1 molar, you couldn't get 1 molar. It's too unstable, you know, it decomposed. And so this reaction is reversible. In other words, this reaction is highly favored to CO2 and water. And so sometimes we show it like this, a big arrow going reverse and a tiny arrow going forward. The tiny arrow going forward says, you know, a little bit of this reaction can occur. The big arrow in the reverse says it likes to go. This side's more stable. Right? And so we could form a little bit of carbonic acid. This is what we call a mechanism. You know, a mechanism just shows you how the electrons get rearranged. In chemical reactions, that's what we look at. You know, how do the electrons get rearranged, or you know, how do the atoms get rearranged? What kind of new bonds do we form? All right, the next example of a Lewis acid-base reaction is water and calcium oxide. And so let me just get you started on this one, and then you can finish this one at home. The reason I want you to help you get you started is because so many people in Chem 1B don't know how to do a Lewis structure for an ionic compound. You know, I found this, even in Chem 1A. But hopefully you guys know how to do a Lewis structure for ionic compound. How do you do the Lewis structure for calcium oxide? Yeah, brackets. Good. How many valence electrons does calcium ion have?
2.
Calcium ion? 0. And then we have oxide. How many valence electrons does oxide have? An octet. And is this a solid? Is it a molecule? What is it?
Solid.
It's a solid. Oxides are solid. And so what do? We make a ionic what do you call this thing again? Lattice. Right? And so this is the solid. This is the surface of the solid. The surface of the solid can be attacked by a liquid, water. And so you tell me what happens as a homework. Okay. All right, let's take a break. Let's take a 10-minute break or so, and then